Relationship between Kw, Ka, and Kb. As you can see over here, this is acetic acid. This is obviously going to be our acid. There obviously needs to be a base for every acid, as we can see over here, and vice versa. If this is going to release, because it is a proton donor, if it releases that and brings it over here, that means this is going to have one less hydrogen, so this becomes now a conjugate base, okay? And this one's going to receive that hydrogen, so it's going to get one more, as we can see over here, so this becomes the conjugate acid. Then we're going to take our conjugate base, as you can see over here, then this now technically becomes our base, okay? Not our conjugate base, it's our base now. That means this becomes our acid, okay? So if this one is going to accept the proton, it's a proton acceptor, it's going to take it from here, then this becomes a conjugate acid, okay? And then what happens here has one less hydrogen, this becomes the conjugate base, okay? So if we actually get this here, which is technically our Ka, because we're dealing with our acid over here, and we just put these products on the top here and these reactants on the bottom here, we get our expression. For Kb, this one over here is technically going to be this one, because we're centering around the base over here, hence the Kb. So this product goes on the top, this reactant goes on the bottom, as you can see over here. The product of these two constants yield what? This and this, right? Our hydroxide and our hydronium, okay? So Kw is equal to this. Why? Technically, hydronium is Ka, technically hydroxide is Kb, okay? Why? Let's prove this. If we get our Ka expression here and Kb expression here, and then we multiply them together, look what happens. This and this cancels out, this and this cancels out, so you're just ending up with hydronium and hydroxide, okay? But what about this Kw as written over here? How can we prove that this is related? Well, we have to treat the equilibrium individual constants as an addition of reaction sequences and show that their product is actually the overall equilibrium constant. How do we know this? Well, let's stack them up each other like a net ionic equation, and we just add them up together here. This one here, they cancel out. This one here and this one, they cancel out. So what do you want to get? And we get 2 moles of H2O over here, and then this adds with this. As you can see, this here would be our Kw. They are related, and it makes sense. So we can actually conclude that Kw is equal to Ka times Kb. That's the conjugate basis for each of the acids. Well, this is the acid, nitrous acid. We have this one over here. And then if we remove this, because this is the acid, right? If we remove this, it's a proton donor, then it's going to have one less. So then we get NO2. We have one less positive, so we're technically a little bit more negative. Now we have to put a -1 over there, okay? So this is the answer. Write the Kb expression for each conjugate base above, okay? So if this is our conjugate base, we're going to add it over here. This becomes a base, and then this becomes the acid. And then, of course, this is going to accept a proton, so this becomes HNO2 again, times the hydroxide, okay, because this one lost that, so it has one less hydrogen, hence over here. So if I get the expression, I put this over here, multiply by that, this becomes a reactant, I put it on the bottom, this here is our expression. Please try these two questions on your own. I'll be giving you the answers shortly. I need help with this chart over here and this chart over here. This is the answer to the first question. This is the answer to the second question.